Okay, so I want to go through, this is a load extension diagram for question 2 on the Leave Insert higher level paper. Okay, so it can either be, it's part of the mechanical testing question, and it can either be a load extension diagram or a stress strain diagram. Now, this is a load extension diagram. The load extension ones are probably the more tricky ones out of two of them, and there's a little bit more to them. So I'm just going to go through it. Now, so here's a question I have. It's from a previous mock exam. The following results were obtained from a tensile test on an alloy of 16mm bar with a gauge length of 80mm. Okay. Using the graph paper supplied, plot the load extension graph and determine 1. The ultimate tensile strength, 2. The 0.1% proof stress, and part 3, I just stuck this one in, I know it says 2 there also. I want to calculate the Young's modulus for the specimen as well. Okay, now so plotting the graph, I have it plotted here just to save a little bit of time. But the way we go about it, the load which is measured in kilonewtons is the top one, the top row on your graph or on your table here. It's always going to be on your y-axis. Okay, so I've spread that along the y-axis. The extension on the bottom is always going to be on the x-axis. Now what I will say is try and spread these out as much as you can. Okay, so see the way I knew the extension was going from 0 to 12. Okay, so I tried to extend it as much as I could out as far as 12 rather than going trying spreading it across a small area. So try spread it out across your page as big as you can. Okay, and the same going in this direction as well. Now, so the first thing on this question is calculating the ultimate tensile strength, or the UTS, for the diagram. Okay, so what is the ultimate tensile strength? Okay, we'll go back up here and have a look. So we defined earlier that the ultimate tensile strength, okay, was the max load over the cross-sectional area. Okay, and the max load is always going to be the very highest point on your graph. If you go back to the question now, and we'll have a look, and we can see that the max load in this question, so on my graph, was this point, and if I look at that on the table, it was the 142 kilonewtons. Okay, so the max load was 142 kilonewtons. So just putting it down here, so we want to find I. Okay, so the UTS. Okay, so I know the UTS is max load over CSA. Now, so the first thing we're going to do is write down our values. Okay, so the first thing we need is our max load. We'll already have the max load, and we know that the max load is equal, and this question we have it, we know it's 142, and it's very important to use the units. Okay, so it's going to be kilonewtons. Okay, so for small k, capital N. Now, so the cross-sectional area is the next one. Okay, so we need to find the cross-sectional area of the specimen. Now, what is the cross-sectional area? So the area of the, in this example, they're asking us to get the cross-sectional area. It's an alloy and it's 16mm diameter bar. Okay, well, so 16mm diameter, we know if it's diameter, it has to be a circle. Okay, so we need to get the cross-sectional area of a circle. So we know the radius for a circle is pi r squared. Okay, we know pi is a constant. We know r. Okay, if the diameter in this case is 16, r is the radius, so it's going to be half the diameter, and it's going to be 8. Okay, squared. You're going to put all that into your calculator, and it's going to come out as, okay, what do we get it as? So it's coming out as 201, I think it was 201.06. okay, and it's millimeters squared. Okay, so 201.06 millimeters squared. So now we have the two values. So we have A, the one the max load, and we have 2 the cross-sectional area. So all we need to do now is plot the two of these back into our formula. So we have max load, which is 142 kilonewtons, divided by cross-sectional area, which is 201.06 millimeters squared. Okay, and we calculate that all out, we should be getting, so 142 divided by 201.06 okay, and we get 0.71, and the unit's going to be kilonewtons per millimeters. Okay, so just bring it over. Because the unit's going to be kilonewtons per millimeters squared. Okay, like that. Okay, so to find the max, or to find the ultimate tensile strength, we know the formula is max load over cross-sectional area. It's very important that it's the max load, it's the highest point in the graph, it's a maximum load, it's not just any load, it's a maximum load divided by the cross-sectional area. Okay, and the cross-sectional area in this case, the area was for a round bar diameter, so we know the cross-sectional area of a circle is pi r squared. Plug it all in, and this is the formula, or this is what we get back from our calculations. Okay, so that's part 1 of the question done. Now, part 2, calculating the 0.1% proof stress. Okay, so what is this? When we're calculating the 0.1% proof stress, we're trying to find the yield point on the graph. Okay, so some graphs have a defined yield point and others don't. Okay, so see here for an example. This is one for cast iron. Cast iron has a defined yield point. It has an upper and a lower point, so it's easy to see. But like in this example here, okay, and in our own graph, there's no defined yield point, so it's kind of one smooth continuous curve rather than a bend coming in it. Okay, so we need to find the yield point. What is the yield point? Well, the yield point is the point, the change from the elastic region of the graph to the plastic region. Okay, so basically after the yield point, plastic deformation will start to occur. Okay, so finding the yield point. Now, so what we need to do, or finding the proof stress. Okay, so to calculate the proof stress from a load extension diagram, first of all, we must draw the load extension diagram, which I have done. Okay, now there's a little bit of work in these ones, so I'm just going to rub this. Okay, so first of all, draw the load extension graph, which we have. Okay, now, second part, we have to enlarge the straight line section of the graph. So I have to redraw the straight line section of the graph. Now, I know this here is a straight line section of my graph. Okay, and the straight line section is always going to be in the elastic region of the graph. Okay, so the first section of the graph in the elastic region. I want to enlarge this section. Okay, so what I need to do, I need to start drawing a new graph. Okay, with the enlarged an enlarged plastic region. So I'm going to okay. Now, so I need to figure out where the furthest points in my elastic region were. Okay, so the plastic region, this was straight point line, and in my diagram or in my question, I know that point was 70.72, and it was load of 72 and extension 0.9. Okay, so I'll maybe go 1 or 2 points beyond that also. So I want to draw the straight line section of the graph, which I know is these first 4 points, and I'll also draw maybe the next one after that as well. So I'm going to draw the graph from extension 0.2 up to 1.5 and load 0 up to 95. Okay, so I'm enlarging the straight line section. So I want to spread it out as far as I want as I can. Okay, I said I'm taking the first 5 points now because that's the straight line section and 1 point after it. So the furthest point in extension I have to go is 1.5, so I'm going to spread this out as much as I can. So 1.5, so maybe I could go 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, and 1.5. Okay, and label the diagram. So this is my extension, and it's in millimeters. Okay, so we said all the extension always goes on my x-axis. Okay. Now, so the load, the highest point on the load we have to go to is going to be 95 kilonewtons. Okay, so I'm going to go up as far as 95. Again, I want to spread it out as much as I can. So I could go maybe 10, 20, 30, 40. Again, I'm just marking them out first without actually putting in the value, so if it doesn't work out, we can change it. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so that works fine. Okay. So now we need to draw in the points. Okay, so I'm taking the first 5 points of my graph. What I will say is fine drawing everything here in pen. You're labeling your axes and stuff in pen. But if you're drawing the rest of your diagram, please draw it in pencil if you make mistakes. Okay, so the first point we're looking at is, okay, this is always going to be 0. Okay, so the starting point of my graph is 0. Okay, so the first point is load 16 and extension 0.2. So find load 16. So here's 10, 11, 12, 13, 14, 15, 16, and extension 0.2. Okay, so that's this point here. Okay, 32 and 0.4 is next. Next is 56 and 0.7. Next is 72 and 0.9. And finally the last one's 95 and 1.5. Okay, so 95. That's going to be this point here. Okay, now I know the straight line section of my graph, so some of these, the first 4 lines should line up perfectly, okay, and they do, because that's going to be my straight line section of the graph. That's the elastic region. Okay, so now I'm going to draw this in pen. What I will say to you is you draw it in pencil, okay, just in case you make a mistake, but just for the visualizer, I want to put it in pencil. Pen. Okay, so that's my straight line section of the graph done. The next part is this curve, okay, I'm just going to put it in pencil first. Okay, I'll go over the pen. Now, so this is the enlarged section of my graph, okay, so that's part 2 of the steps done, okay, so I'm after enlarging the straight line. Now, I need to find 0.1 or 0.2% gauge length of the sample, okay, so what this means, so depending on the question, if it's 0.1 or 0.2%, in the question here they're asking us to find 0.1% of the proof stress, okay, so I need to find 0.1% of the gauge length. So we're told the gauge length is 80. So 0.1% of 80 millimeters, and that is equal to 0.08 millimeters. Okay, so that's 0.1% of the gauge length. Now, the next step I need to do is I need to find that on my graph. Okay, so where is that? So I'm going to find 0.08, sorry, down here. So here's 0.2. This is 0. Okay, so this is 0.1 here. So 0.8 has to be the box before it. Okay, so I'll just zoom in there. Okay, so 0.08, and I know it's the little box here before it. Okay, from there I want to draw a line parallel to the straight line part of my graph. Okay, so a line parallel to that. So the easiest way to do this, the way I always do it, is I know that to get that 0.08, okay, so to get this point, I measured out from the 0, I measured out 1, 2, 3, 4 little boxes. Okay, so I'll take another section on my graph and measure out 4 little boxes. Okay, so on the straight line. So maybe take this section here. Okay, I'm going to measure out 4. So here's 1, 2, 3, 4. Okay, mark it off, mark the little point. And then when we do that, we're going to join them 2 lines, and that means that the 2 lines have to be parallel to each other. Okay, I'll just put this in red pen. Okay, so now this line I'm after drawing in, okay, is parallel to the straight line section of the graph, and it's also coming from 0.08, which is 0.1% of the gauge length. Now, where this intersects my graph or my line, I'm going to draw a horizontal line straight across. Okay, so from that I'm going to find horizontal line. Okay. Like this. So now the value I get here is going to be what's known as my proof stress, okay, or proof load or proof force or proof, it's going to be my proof load or force, okay. So that point there, and we read the value, okay, and it's coming out as 85 kilonewtons, okay. So my proof stress or proof force is 85 kilonewtons. Okay, so what does this mean? Now we need to put this into our formula, okay. So we know that the formula for proof stress is proof force divided by cross-sectional area. Okay, so PS equals PF, which is proof force, over cross-sectional area. Okay, proof force, we have to calculate it out. To find the proof force, we have to draw a line parallel to the straight line section of the graph from the 0.1% of the gauge length, which we figured out was 0.08. So I enlarged my graph, got 0.08, draw a parallel line to the straight line section of the graph. Where that intersected my curve, I brought this back to find it on my y-axis or my load axis. Okay, I got the value is 85 kilonewtons. So my proof force is 85, okay, kilonewtons divided by the cross-sectional area. So this is the cross-sectional area again. So it's going to be pi, okay, 8 squared in this case, because the 8 is the radius of the diameter bar. Multiply that out, okay, and we're going to get, so we get 85 divided by, okay, and we're going to get 0.42 kilonewtons per millimeters squared. Okay, and that's how we find 0.1% proof stress on a load extension diagram. Okay, it's a little bit different for the stress strain diagram. It's a little bit more simpler in the stress strain diagram, but this is how you find it for a load extension diagram. Okay, so finally then, the last part we're looking at is calculating the Young's modulus for the specimen. Okay, so the Young's modulus. What did we say the Young's modulus was? Okay, so go back up here. So we said the Young's modulus of elasticity is in the elastic range of material, stress is directly proportional to the strain. So Young's modulus is the stress divided by the strain. Now please note that the stress and strain values for the Young's modulus can only be calculated in the elastic region of the graph, hence the straight line part of your graph. Okay, so it can only be calculated in the straight line part of your graph. So we need to find the Young's modulus, so stress over strain. Now what's the formula for stress? Okay, so the formula for stress is load divided by cross-sectional area. The formula for strain is extension over the original length. Now, so bringing it back to our question here. Okay, so I'm going to rub this one. Okay, so we want to find the Young's modulus. Okay, so the Young's modulus is denoted sometimes by just the simple letter E. Okay, for elasticity, so E equals stress over strain. Okay, so this is 1, this is 2. Now, so I need to find, the first thing I need to find is these two values here. So first I need to find the stress. Now, so stress, okay, we said that the formula for stress was load divided by CSA. Okay, so load divided by CSA. Now, I said that this has to be calculated in the elastic region of the graph. From this, I know that these first couple of points are in the elastic region. What I do always say is when we're calculating the Young's modulus, always take the second point in the graph, okay, because we know that's definitely in the elastic region of the graph. Okay, so I'm going to take the load as 32 and the extension as 0.4. So the first thing is the load, 32. So I know the stress here is 32. I know the cross-sectional area, okay, from calculating it out earlier on, is 201.06. Okay, so that's 32 kilonewtons, and that's millimeters squared. Okay, so bring this, calculating this out, so 32 divided by 201.06, okay, and I get my answer as 0.15 kilonewtons per millimeters squared. So that's part 1 of my formula completed. Okay, so part 2 then I need to get the stress now. So the stress, okay, and we said the stress was extension, okay, over the gauge length. Okay, so I'm just going to call that GL for gauge length. Okay, so what's the extension? We took the second bar to the graph. We said we're taking the second point, so the extension in this case is 0.4. Okay. The gauge length in this case is 80 millimeters. Okay, so that's 0.4 millimeters. The gauge length is 80 millimeters. Okay, so we break this down then and we get, okay, if we get 0.005. Okay, now the stress is a ratio. Okay, so there's no unit to it. All right, now I need to put the two of these back into my formula. Okay, so I have part 1 of the formula, which I know is 0.15. I have part 2, the strain, which I know is 0.05. Okay, so let's put all this back in. So E, so stress we calculate as 0.15 kilonewtons per millimeter squared. Strain we said was 0.005. Okay, so 0.15 divided by 0.005. Okay, and we get it to be 30. Okay, and the value is going to be 30 kilonewtons per millimeters squared. Okay, so that's how to calculate the final part, and that's the Young's modulus for the specimen. Okay, generally these are all, if you know how to calculate the 3 of these, so tensile strength, proof stress, and Young's modulus for the specimen, you know what to do with the majority of the question. Okay,